This video lecture is part of a series that introduces diodes from a circuit perspective, and there was a first lecture that covered basically the ideal diode behavior, that of being an open or closed switch. We introduced the Shockley equation diode, which provides an exponential relationship between diode voltage and diode current. We then looked at some real diode IV curves, specifically the 1N4148 little signal diode, and found that to accurately model the diode at higher currents, we needed to add in a series resistance. And then we lastly fit a Shockley plus resistance model to the datasheet IV curve of a 1N4148, and we produced a SPICE circuit model for the diode, and then replicated the IV curve in SPICE. In a second video lecture, we took a look at a 1N4148 datasheet, just to gain some exposure to some of the other real-world characteristics that are associated with the diode. That second lecture is not critical for this lecture, but was just kind of for broader understanding of a real diode. What we want to do in this lecture now is to move on to point 4 here, where we are going to develop, or actually we have developed some of these models already, but we're going to lay out kind of a set of diode models from simplest to a little more complicated, and those will be the models from which we will pull from whenever we analyze a diode circuit. In a future lecture, I will introduce the small signal diode model, which is basically a means of replacing, when you're trying to look at just how the voltage across the diode changes incrementally due to an incremental current change in the diode, you can use a small signal model, which essentially replaces the diode with the resistance. And so I'll do that in a separate lecture, and then as a final lecture we'll just work a number of diode circuits and apply these various models and small signal techniques when necessary to solve those circuits. So for now, let's introduce several simple diode models, and we're going to look at a total of 4 of them. Let me scroll down to a new spot here. Okay, here is a table of the models that we will be discussing, and so we have already introduced a couple of these. Right, so the first model is just the ideal model, and that is the idea that it is a switch. All right, it's either a short or it is an open, and the conditions are, if the current flowing through the diode is positive, then it's a short, and the voltage across it is 0 at that point. And if the voltage across the diode is negative, then it is open and there is no current. It's an ideal model. It is the most ideal diode model that we can use. In the next model, or the next one that we talked about, actually is the Shockley diode model. All right, and here I show the Shockley model that includes a series resistance RS. Okay, so the voltage across the Shockley diode, remember I put a little S there to show that it's the VI of that diode is modeled by the Shockley equation. The total voltage across our diode model will be the Shockley voltage, that is this N times Vt log of the current divided by the scaling current, plus the voltage that's developed across RS, right? So RS times ID. So we'll have both of those. We introduced that model at the end of the first video lecture. Now, what we haven't talked about are these two middle models. And here's the idea. If you start with the most ideal diode model, which is just a short, you quickly encounter the issue that, well, okay, there's clearly some voltage across the diode when it conducts. Okay, it's not 0. So instead of saying that it's 0 volts when it conducts, let's say it's some fixed amount of voltage. All right, and typically that voltage is around 7.7 volts. Let me draw a VI curve, okay, for a diode. Now so far in the video lectures I realize we've only been plotting the VI curve on a semi-log scale, so it's been voltage versus current. Current is on the is a semi-log, is on a log scale. So make sure I plot the right thing here. Yeah. So this is what the diode curve would typically look like if you have it on a linear scale. It looks like 0 for a long time, and then it goes up really steeply. Let me try that again here. Okay, it goes up really, not that, it doesn't curve back. Okay, so just leave it like that. Kind of goes on. So what we can do is our ideal model, okay, our ideal model is just that it's a straight line, right? When it's on, it has no voltage drop, and then when there's negative voltage, it has no current. This is the ideal diode. And here we say, hey, wait a minute, we should add a little bit more. How about if we just shift this curve, and we'll just say that it still has a vertical line like this, but instead of having a voltage of 0 volts when it's conducting, we'll say that it has a voltage of, say, 0.7 volts. Okay, so we do that by adding in a voltage or a battery in series with an ideal diode. So notice here I've got the little I for ideal. So that's our one step closer to reality from a purely ideal diode. All right. Now, after we do that, we look at the model and say, hey, wait a minute. The real diode has a finite slope. It's not an infinite slope like our orange line there. So what if we actually made a model that followed this line? It's going to be hard to draw on here. Followed this line, had some finite slope, and it crossed here. Let me change the color on that to do red. Okay, so yeah, so it would be like this. Okay, so it has some slope, and that slope actually has units of 1 over ohms, and we'll say it's 1 over, what did I call this? 1 over RD, capital RD, and then we'll say VDO for this voltage here, VDO. Okay, so the way that we make that model is with a constant, we'll call it a constant slope diode. Let me color these in here. Oops. Yep. Okay. So we've augmented our model, our second model, by adding in, this is what's added, and this is what's added. So as we move to the right, we added a battery, and then we added a resistance. Okay, and again, the accuracy of this model is going to depend on where you are working in the IV space. So if you're operating, say, down at a really low current, let's say you're operating way down here in your circuit, well, then the the battery plus resistance model is not going to be very accurate. It actually says at this point that the diode is off. But assuming that you're operating maybe in this range here, then that diode may be sufficient. That model may be sufficient. Okay, so it's not black and white in terms of picking these model parameters. You really need to have some confidence or knowledge about the circuit that you're going to be using this diode in. And that may make some of you uncomfortable because you think, okay, what is the right answer? Well, it all depends. And sometimes you don't know what the operating currents in your circuit are going to be until you actually have a model. So maybe one way of addressing this is that you actually first create a Shockley plus resistance model, and maybe through a simulator you simulate the circuit and determine, okay, this is the current that's going to be flowing through the circuit, and then maybe with all the, if you have some varying parameters like the battery voltage is going to change over this range, you end up getting kind of an operating current range for this diode and say, okay, it's going to operate between 10 and 20 milliamps. And then you can come back and create a model like the battery plus resistance model that fits it well over that range. And now you have a simple model that will allow you to do a linear analysis on your circuit, but still do a pretty good job of predicting the actual current and voltage of the real diode. Notice that the first three models, okay, these here are all linear models. Now, strictly speaking, adding a battery in series to and make it part of a two-terminal element results in the element itself not being linear. However, if we treat this battery as actually one of the other voltages sources that drives the circuit, and you throw it in an otherwise linear circuit, it does not negate the linearity of the overall circuit, and we'll see this by solving some circuits later. Okay, so this is these are basically the. So in a future video lecture, we'll use these models to actually solve some circuits, and that's probably the best way to really become comfortable with them. So at this point, I've described the four models here, but haven't really given too much insight on how you would actually pick the values. We did look at this IV curve, and hopefully that was insightful or helpful. But what I want to do now is run through each model and just discuss how you might pick the parameters for populating that model. Of course, the ideal model, ideal diode, has no parameters because it's 0 volts or open circuit. The constant voltage diode model does require one parameter, and that is whatever we'll call it the V on voltage. And that really depends on where you're going to operate the diode. And my suggestion is, if you're given a problem where the nominal voltage, nominal current through the diode is going to be, let's say it happens to be 10 milliamps, okay, and then I would look at the diode curve. Presumably you would be given a diode curve, or you'd be given a diode equation, and you would then determine what the voltage is at that point. So, for instance, if you're given, oh, this is an N equal 2, IS equal 10 to the minus 9 amp, and RS equal to 0, let's say in this case, then you could say, well, the diode voltage is going to be N times VT, and then they'd say, oh, and this is at room temperature that we're going to do this analysis. Okay, so you'd have N, which is 2, VT, which we'll use 25 millivolts because it's room temperature, times the log of the current 10 milliamps divided by 10 to the minus 9 amps, right? And you would evaluate that and find some voltage, okay? So in this case, VD evaluates to about 806 millivolts, okay? So then your model might just simply be an ideal diode and a 806 millivolt battery, right? So the idea is that here's the curve, and here is ID, and the operating point is 10 milliamps. So find what voltage that is, and then just pick your model to just have a voltage equal to that particular voltage, 806 millivolts. Okay, so that's how you'd pick the model parameter for the battery, the ideal plus battery constant voltage model. Let's now look at the constant slope diode. So in this case, we are looking at the model that includes a resistance RD. If we look at our diode IV curve, it corresponds to the red line here, where we still intersect, say, at our operating point, but then we actually want a finite slope rather than a vertical slope. Now, if you're going to be operating over some current range, you may not want to actually have your model fit the actual diode IV data point right at your nominal operating point. Okay, so for instance, if you had something like this and you needed to fit over a range, okay, then, and if the range of current was somewhere between here and say here, okay, then perhaps you would want, and your nominal operating point was right here, you may not want to have your model exactly fit the curve at that point because you're trying to minimize error over that whole area. So this is, you know, if you're typically you'll do it, you'll eyeball it, and you'll get something that's close enough, but there certainly isn't a singular answer to it, unless you can do this analytically, where you say minimize, you know, minimize the maximum error over the range of whatever it is, 1 to 10 milliamps. But typically we don't get that that specific about it. So let's just say in this case we are happy with just our constant slope diode intersecting the exact diode curve right at our operating point. Okay, so we need to have this finite slope, which is RD, and we have an x-intercept of VDO. Okay, so our model then is going to be VDO and RD. Okay, the question is, what is VDO? So VDO, if I draw this down here and I put, you know, we look at what is the difference between VDO and our operating voltage VQ, right? VDO. The difference is going to be our IQ, right? IQ times the slope. Okay, or I should say no, maybe it's not. It's going to be the slope, 1 over RD, divided times 1 over IQ, right? So we can write VDO is going to be equal to VQ minus, that's not right, can't be right, that's RD times IQ, right, for proper units. So we'll have VQ is equal to, I'm sorry, VDO is equal to VQ minus RD IQ. Okay, another way that you can draw this is, okay, because this will have an open circuit of VQ minus RD times IQ and a Thevenin resistance of RD. Now we could redraw this as a voltage source that is at VQ, okay, and we still have RD, But now I'm going to put in a current source, right? IQ. Okay? So what does this do? The idea is that when IQ flows into our diode, we want a voltage of VQ. And in this case, that's exactly what will happen, because if IQ flows in, it's going to flow in to this junction here. And we have IQ going in, we have IQ going out. And that means there must be 0 going through here. Okay, and if there's 0 current going through RD, then there's 0 volts across it. And so the voltage, overall voltage across the Thevenin or the diode terminals are simply going to be the 0 volts across RD plus VQ. So you can draw the model either way. These are equivalent. Okay? And in some ways, this makes more sense. This one makes more sense to me because it involves just VQ and IQ, right? And but however it makes sense to you, either way works fine. So the way you would pick this, let's say that let's say I use this second representation right here. If I want my model to fit the data right at my operating point, then I know VQ and IQ, right? And the only thing left to pick is I need to determine what the slope of this line is right here, and then take the inverse, and that will be my RD, which I will place here. Okay, the last model we're going to look at is the Shockley plus series resistance. This model we actually already looked at in the first lecture. We actually looked at real data and showed how you can pick the parameters of the Shockley diode, primarily N, the emissivity constant or ideality constant, and IS, the scaling or saturation current. And you could pick that from the diode curve if you plotted it on a log voltage versus, linear voltage versus log current plot. And then you looked at the low level currents where any voltage across RS would be very small. Then you looked in the higher current region where you saw an excursion in current. Let me just actually scroll up to that. It's right here. And at the higher currents, you see that the straight line of the Shockley equation no longer predicts the actual voltage across the diode. And so that difference, in this case for the 1N4148, it's 400 millivolts out at 800 milliamps. And so the error in the Shockley model is 400 millivolts, which must be across a series resistance RS, and that occurs at 800 milliamps. So the resistance is estimated at 400 millivolts divided by 800 milliamps, or a half an ohm. Okay, I think I will stop here and talk about the small signal model next, and then we'll have a video lecture on just working some examples.